So 5.2, page 116, talks about quantum numbers. Now, what are quantum numbers? Well, to completely describe an electron's position in an atom, 4 quantum numbers are needed. So quantum numbers are kind of like an address for the electron. So if you think about your address, right, where you live, that's where you are found most of the time, right? It's where you sleep, it's where you eat. During the day, you might be at school or wherever you are with your activities, but most of the time, you are at your house. And the quantum numbers for an electron are basically the electron's address. Now, in our address, right, we include our province, our city, our street, and then our house number. And so I picked these 4 main things because this is sort of mirrors the quantum numbers for an electron. The province is obviously our large general area, and then the city is a specific part of the province. Our street is a specific part of the city, and our house is a specific part of the street. And so if we look at the first quantum number, it's represented by n. So you might see n equals 1, or n equals 2, or 3, or 4. And that is the energy level of the electron. So that's kind of the largest sort of category of the quantum numbers. It's the general energy level. And if you look at the periodic table over there, you'll see the numbers on the side for the rows, and those are generally if you look at those are the energy levels. So I'll talk a little bit about that. But you have hydrogen over here, and you have the metals, alkali and alkaline earths, and you have a 1 beside hydrogen, going this way, and you have a 2 and 3 and 4 and so on. And generally, these are the energy levels for the rows. Now, we'll find out a little bit later that some electrons that technically, are in, let's say this row right here, they're not in the 4th energy level. They're in actually the 3rd, but that's coming a little bit later. I'll explain that a little bit later. So n is the energy level. In each energy level, the greatest number of electrons that is possible to exist in that energy level is 2 times n squared. So in the first energy level, if n equals 1, the maximum number of electrons that can exist in the first energy level is 2. Okay? In energy level 3, the maximum number of electrons that could exist there would be 18. Okay, so that's the maximum number of electrons that can exist in that energy level. Now, another way to think about it, which is maybe, I don't know, it's a little bit awkward, but I like to think about it as a hotel, except this hotel has a really small first floor. N equals 1 right here. N equals 1. And then the second floor, so how many electrons would exist in the second floor? Second electron, or second level? 8, okay? So then you've got, a floor like this here, that can have 8. This is maybe 1 room with 2 electrons in here. And then you can have, some more rooms here, you have 8. Then you have 16. So it's kind of like a hotel that has, can fit more and more electrons as you go up instead of the other way around. But it's sort of like that. You can only have 2 electrons in the first energy level. You can only have 8, 3, 4, 5, 6, 7, 8 electrons in the second level, and so on. Okay? And this little analogy will help when we talk about filling order. Okay? We talk about filling order and where electrons go and where they come out from and stuff. Yeah, I don't know. They may be referred to shell order somewhere. I've never heard that, but in some literature that might be the same thing. So anyway, just a little analogy for you to think about as we move through this. So the second quantum number, if we talk about the second one, okay, its letter is L, and it describes the sub-level within the energy level. So you'll hear this word sub-level a lot. So you have an energy level, and then inside the energy level, there are sub-levels. Now, these sub-levels are types of orbitals. And we talked yesterday about orbitals are the specific regions that electrons can occupy. And these types of orbitals are represented by letters. Okay? So you have the energy level, and then you have the type of orbital within that energy level that the electron is occupying. So far the address, we've got the electron is going to be in some energy level, n equals whatever, and then inside that energy level, an electron is going to be in a specific orbital. And of course, if we just zip back real quickly, there's an orbital, right? This sort of hourglass-shaped orbital. We're going to find out what that one's called. And then, of course, we talked about a spherical, orbital as well, just a round one, right? Spherical. And so these are the sublevels. Where are we? Right there. So the s orbital is spherical. That's kind of nice. S stands for spherical, I guess. The s orbital is spherical. So it's just a little, a ball. So the electron flies around the nucleus and, just forms a nice round spherical, shape. The p sublevel, that's the p sublevel or p orbital, is an hourglass shape. And these are the two that I sort of drew yesterday. So we have, a bit of a spherical, sublevel, and then you have a sort of hourglass shaped sublevel. Looks kind of like this, two lobes, right? And this is sort of the p sublevel here. Okay, so that's an s here, and here is a p orbital. It's one orbital that looks like an hourglass. Now there isn't a 1p orbital. There isn't a 1p because there's only 2 electrons allowed in the first level, and so it only has an s. Okay, and this one here is not a sublevel. There are 3 p orbitals, and so this is one of them. Okay, this is one p orbital right here. Another p orbital would be the same shape, but oriented this way. Okay, perpendicular to this one. And then the third p orbital, you have to think three-dimensionally now and think about the orbital kind of coming out at you and then going back behind as well. Okay, so this one sort of three-dimensionally kind of comes out here and back there, right? So we would have, I can try and explain this. This would be the px orbital. Why? Because this would be like the x-axis. Think about math, right? This one here would be the py orbital, the one that's oriented along this y-axis. And then the one that goes in, out here, I got a lot of blue there, but the one that goes kind of in and out like this, that's the pz. So x, y, and z. So it's the z-axis there, coming in and out. So if you think about the screen there, right? We have x sideways, we have y straight up and down, and then we have the z coming straight out from the board, right? And then going back into the wall as well. All right, the next one we're going to talk about is the d orbitals. So s, p, and d orbitals. And there are 5 different d orbitals in each sublevel that they exist in. And they have different shapes. So we're going to talk about the shapes of d orbitals a bit later. Okay, we will go over the shapes of the d orbitals. You have to memorize those. But those are a little bit more complicated. So we're just going to focus on the s and the p for now. But just to let you know that there are other orbitals that we're going to talk about a little bit, and they're f orbitals. These are very, very complicated. We're not going to make you memorize the shapes of those or be able to reproduce those from memory. But we will just talk about where those orbitals, what electrons would occupy those orbitals. So we're going to have to look closely at s and p, later at d, and so on. Okay? So the energy level is the first quantum number. Then second quantum number is the type of orbital or the sublevel. The third quantum number, so remember there's 4 aspects to the electron's address. The third quantum number is given by the letter m. We won't use these letters a whole lot, I'll just be honest with you. But m would be so if you see m equals, right, that's the third quantum number. It describes the specific orbital that the electron is in. And I already actually showed you that third quantum number earlier, without you even noticing, but they are, x, y, z, squared, and etc. So if you think about the x, y, and z, the first 3 there, I attach those to the p orbitals that I drew for you. Okay, so the third quantum number describes the specific orbital because there's more than one sublevel in most energy levels. Okay, so I'll say that again. The third quantum number describes the specific orbital because there are more than one sublevel in many of the energy levels. So we have energy level, and then we have the type of orbital, and sometimes that type of orbital, there's more than one. So we need to distinguish between them, and that's where this X, Y, Z comes in. Okay? So let's say that this is a 2pz orbital right here. This I'm outlining it in black here now. That's kind of the one that goes in and out from the board, right? This one right here. So here's your first energy level right here, or the first quantum number. There's the second quantum number. There's the third quantum number. And yes, they are letters. They're still called quantum numbers. Okay? So 2pz, that's three quantum numbers right there describing where this electron is. Second level, p-shaped orbital, and it's the Z orbital. Okay? All right. Now finally, the fourth quantum number. The fourth quantum number is given by the letter S. And this states, okay, so we no longer have really a region or a place to place the electron. Like there's no more, there's no other aspect of the electron's address that we need to talk about as far as a region. This one now is called the spin. You'll hear it as the spin or angular momentum, but mostly spin. That'll be the common thing we talk about. And so it's a really kind of tough to think about, but two electrons can exist in any orbital. Only two. And in order for them to be in this same orbital, they have to have opposite angular momentum. They cannot be spinning the same way. And so and again, this is a model, right? We think about this as spin. So an electron, if we're thinking about, let me just draw this over here. If we're thinking about an electron here, okay, and it is spinning this way, okay? So you think about it flying through space, it's moving, and it is spinning on its axis one way. The other electron that may be in the orbital, okay, would be spinning the opposite way. Okay? So if they are to exist in the same orbital, let's say this is an s orbital, the electrons themselves have to be spinning in opposite directions in order for them to kind of balance out and exist. So the number that is associated with the fourth quantum number is either a positive 1/2 or a negative 1/2. Okay? Positive 1/2 or negative 1/2. That's just the number that they attach to the spin. So, and positive, negative, that just means that they're spinning opposite ways. Okay? And any two electrons, again, I'll say this again, that occupy the same orbital must spin in opposite directions in order for them to be stable. Okay? So, that's it. That's the four quantum numbers. And here's your example here. If we have an electron with the quantum numbers 3, D, and then the XY is the third quantum number, and that's written as a subscript always, okay? A subscript. Positive 1/2. These are the four quantum numbers. So we have energy level, 3. We have sublevel, D. Okay, we have specific orbital, the XY, the DXY orbital. And then we have our spin. So there's the four aspects. Okay? Okay, shapes of orbitals. So orbitals and suborbitals of bound electrons, so the electrons that exhibit the orbitals. Now, S is our first one, right? And we said it's spherical. Okay? That's great. It's just a ball. It's a region of space that's spherical. What you have to understand, I guess, is that if we're talking about the 1s orbital, it's a small sort of ball. Okay? The 2s orbital, and there's 1s, there's 2s, 3s, 4s, 5s, 6s, okay? There's s orbitals in each energy level, and they keep getting sort of larger, okay? So the 2s is a larger sort of spherical region. And then, you know, the 3s would be larger even yet. Still spherical, okay? Still, you know, centered around the nucleus, but larger, okay? So you have 3, spheres, there's one on the inside, electrons stay in there, and then the 2s would be quite a bit larger, and those electrons stay in that bigger region, and 3 and 4 and so on. Okay? So they can exist all at the same time. If you have lots of electrons, then they will fill the 1s, okay? They'll fill the 2s and the 3s and so on. Okay? Spherical. Now the p orbitals, this is a picture of all of them at once. All right? So as I mentioned here, we talked about the p orbitals. This is what it would look like if all the p orbitals had electrons in them. That's sort of the what it would look like, right? All the electrons whirring around in all 3 p orbitals. That's what it would look like. So you can see I've already done a little bit of scratching here before with class before, but we would have 2 electrons. Now they don't necessarily stay one in each lobe. They all fly around. Okay, they both fly around here, but they form this region. And the x would be aligned along the x-axis, the y and the y, and the z and the z. Does it matter if you put the x as this horizontal one? No, it doesn't matter. As long as you realize that there's the 3 different orientations, right? So x can be like this, y can be like this, z can be like this. Doesn't matter. Because it's 3-dimensional, right? If you look at this object, okay, right here, if I spin it upside down like this, still the same object. You're just looking at it a different way, right? And so, same thing. You can draw your x-axis going up and down if you want, or side to side. Doesn't matter. But just know that the p orbitals are oriented on the 3-dimensional axes there. Okay, good? All right, the d orbitals. Okay, let's talk about the d orbitals, and I just feel like maybe I need to zoom in here just a little bit more. Yes, you will need to draw these. You bet. Yeah. Okay, let's see how much I can zoom in here so you can see them. Okay, we'll take our time with the D, okay? Now, you do not have to draw this because that's like, well, you don't have to draw that. That's all of them at once, right? So you just don't even worry about drawing that. But let's draw the each orbital, okay, each orbital separately. So the first type of orbital, and again, that we're going to look at here is dxy. There's no specific order, doesn't matter, all right? dxy. So why is it called the xy? Because the d orbitals, most of them as you see, this one, this one, this one, and this one, are all 4-lobed orbitals. So they're kind of like 2 p orbitals stuck together, right? So that's what a d orbital looks like. This one's the exception. But over here, you have the orbitals like this, the 4 lobes of the d orbital, extending like this. And the reason why it's called the xy orbital is because the lobes extend between the x and the y axis. You see that? They're between. On all 4 sides, they're between the x and y. Okay? So the dxy orbital is a 4-lobed orbital, and the lobes are centered obviously at the middle, at the origin of what the axes would be there when we're drawing them. That would be about the nucleus, right? And the lobes extend in between the x and y axis. Okay? The dxz, as you can probably guess and see from the diagram, it's another 4-lobed orbital, and it extends between the z, the x, and the z. So here's the x orbital, x-axis. Here's the z-axis, just so you can see that. And these orbitals, of course, exist in between. A little tougher to draw, right? Okay, but when you're drawing them for an exam, right, or for your test or whatever, you just draw the axes however you want. You can draw the x and y just like this, as long as you write them like this, right? And then here's your orbital. You just go 1, 2, 3, 4, like a butterfly. And that's your orbital. That's the dxy orbital. Okay? This diagram is showing you the same perspective. Okay? It's one perspective, and they're showing you all the different orbitals, how they are arranged. But if you're drawing them, okay, watch this. You can do dxy like this, or you can do the dxz, okay, the dxz that we just drew, and you can do it like this, and you say, okay, well, I'm just going to make this the z-axis. There you go. That's the dxz. All you're doing is you're showing me that the orbital The lobes are between those two axes. Get that? Okay. But this diagram right here just shows you kind of from one perspective. All right, I'll leave that there. I'm going to erase this so we can move on. The other one here, the third one, dyz, you got it. It's just, here's the z, here's the y, 4 lobes in between. Okay, you're going to draw yours a little bit more careful than mine here. I'm just kind of outlining them for you, right? But between the x and the z and the y. Very straightforward. Those three are all the same. Now this one here, okay, don't ask me why they've got x squared minus y squared. Don't really know why. There probably is a reason. I don't really know that offhand, but this is the third quantum number here for this orbital, x squared minus y squared. And these are on the axes, okay? So these 4 lobes, still 4 lobed, they are on the axes. And which ones? On the x and y axes. So the x goes right through those 2 lobes, and the y goes right through these 2 lobes. So finally, that brings us to the final d orbital that we need to study. And as you can see, this one is quite different than the other 4. This is the dz squared orbital. And yes, this is the z-axis that the bulk of this that it's aligned with, right? Now, it's sort of like a p orbital. It's actually just like a p orbital, except it's got an additional sort of donut shape region as well around the middle. Okay, so that's what the dz squared orbital looks like. The f orbitals, okay, the f orbitals, if you look at your periodic table, what you see is down at the bottom, the lanthanoids and actinoids, right, or the lanthanoid series and the actinoid series. These ones down here, okay, this is where the f orbitals are. And I'm going to go over the periodic table here with you again and show you where the electrons that are in these orbitals, where they're found. But the f orbitals are special, and these are for, they're obviously a very high level of, where the electrons occupy. The shapes are very, very complicated, so we're not going to study those shapes. But these are the f orbitals here, that one and that one, those 2 series. So I'll go over the periodic table a little closer with you here right away, and I'll show you where the orbitals that are in these, where the electrons that are in these orbitals exist. So that's why we're not going to show you the f orbitals, because they're just too complicated right now for you to learn. So back to our notes here, we are going to talk about filling order right now, and the filling order, basically the filling order is, when the electrons are in an atom, okay, which orbitals do they occupy? Is it like, any electron that comes in can pick any orbital that it wants and it just kind of goes to that orbital? Not really. No. There's a specific order in which electrons fill orbitals. The first orbital that is filled is always the 1s. So if you think about a hydrogen atom, okay? Hydrogen atom, right, has 1 electron. That electron does not get to pick any of the orbitals that we've just talked about here. It has to go in the 1s. Okay, it goes in the 1s. Now, if the orbital has energy added to it, if it is excited, that's the technical science term for it. If you excite that electron and give it more energy, it will jump to a different orbital. But in its sort of ground state, in its most relaxed, natural state, that 1 electron will just have a kind of a minimal amount of energy, and it will stay in the s orbital. Okay? So again, that's kind of the natural state. The first orbital goes in the 1s. The second electron goes in the 1s as well. Remember, each orbital can have 2 electrons. I think that's in the notes a bit later. But if we're talking about filling order, it's the 1s first, then the 2s. Okay? The second orbital that's filled is the 2s. And the third is the 2p. And we can know this filling order by looking at the periodic table. And this is the easiest way to know the order of the electrons that fill. So for example, let's say we're talking about silicon. Okay? Silicon. How many electrons in an atom of silicon are there? 14, right. There's 14 electrons. How do I know that? Because silicon's atomic number is 14, and in a neutral atom it has to have 14 protons and 14 electrons. Okay? So if we look at silicon's 14 electrons, you know, how do we know which ones they fill? Like, just do they fill the 1s first, and then do they go to the 2s, or do they do 1s and then, you know, a p orbital, and then back to a 2s, and then to this? How does that work? So that's what we're going to look at. All the 14 are filling orbitals in a predictable way. So we'll go back to our periodic table. All right, so on your periodic table, feel free to kind of drop this down in your periodic table. But what we have here is we have the rows. Remember I said that the energy levels are roughly the rows of the periodic table? And so you can do this, just write you know, the energy levels down here, 1 through 7 for each row of the periodic table. And so yes, the first energy level can have 2 electrons, we talked about that before, and the electrons fill the 1s first. So the 1s is, and I'm gonna outline the elements on the periodic table. So that would be the 1s. One electron would go here, and the other electron would go over here in helium. All right, just ignore this for now. That's not necessary in the periodic table. That other hydrogen here, just forget about that for now. But this is the 1s right here. 1s. So it's this one and this one here. So you can look at the periodic table and look at the first row, and there's only 2 elements on the first row, right? And that is the 1s orbital. Now hydrogen, we said, has 1 electron. So here's hydrogen, right here. And you know that its 1 electron is going to exist in the 1s because everything has to start right here, the top left. So that 1 electron is going to be in the 1s. For helium now, okay, if we look at helium, over here, how many electrons does helium have? Well, there's 2 protons, so 2 electrons, right? One of helium's electrons is going to be in the 1s, and the second one also is going to be in the 1s. So helium has a full 1s orbital. There's 1s orbital, and there's 2 electrons in there, and that's a notation I'll talk about a little bit later. But it has 2 electrons in its 1s orbital, and its 1s orbital is completely full. Okay? Good so far? So, first electron, second electron, both go in the 1s. Now, so that's kind of left to right, like we'd read a book. Now we go to the next row. Here we have energy level 2. And guess what? This is the 2s orbital right here. 2s. 2s orbital. So the electrons for lithium and beryllium, okay, they have electrons in the 1s and the 2s. So the filling order goes, let's do lithium, okay? We have 1 electron in the 1s. And do you remember when I was showing you electrons, when I was drawing the spin, that I kind of drew the electrons like this? This is how you draw electrons, one of the ways. And this would be a positive 1/2 spin. That's how you'd represent an electron with a positive 1/2 spin. You kind of put a little tail on the top there, and this would be a negative 1/2 spin. So that's how you would signify or show that you have 2 electrons in an orbital. So this is your 1s, okay? We have 2 electrons in there. So it has the 1 and 2. Where's the third electron go? Well, in the 2s. So there's a 2s orbital, and it's got an electron in there too. And you can write that as 1s has 2 electrons in it. The 2s is filled next, and it has 1 electron. Lithium is atomic number 3. It should have 3 electrons. There's 1, 2, 3. Here's 1, 2, 3 electrons. Okay, you getting that so far? I'll do lots of examples, so it'll start to take shape a little bit more for you. But as we move through the periodic table here, okay, so beryllium would have a full 1s and a full 2s shell. Okay. Now over here, use a different color. But over here, we're still in energy level 2. But what orbitals do you think these might represent? What would be next after the S? No, P actually. Yeah. So these are the 2p orbitals. The 2p orbitals, okay? So if we look at neon, let's look at neon here. Okay? I'm kind of running out of room a little bit, so I'm going to erase some of this stuff here. Let's say we look at neon. And what does it look like? Well, it would have, and you start from the very beginning. It has 2 electrons in the 1s. Okay, let's show that. 2 electrons in the 1s. And then we're going to go back over to the left. It has 2 electrons in the 2s. Here's the 2s, and it has 1 there and 1 there. And then it has 1, 2, 3, 4, 5, 6. You see how I stop counting when I get to the actual element on the table? Right? So we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 electrons in total. And in the 2p orbitals, so these 6 represent all of the 2p orbitals. It would be like 2px, 2py, 2pz. And so it would look kind of like this. So this is going to get a little bit busy, but I'll try. Here's the 2pz. Here's the 2px. And the 2py would come out like this, or whatever, x. You can put this y and this x, this z, doesn't matter. But you see how those 3 orbitals are there as well? And we have electrons. We have 1 here, and 1 here, 1 here, and 1 here. So 2 in each orbital. And yes, these diagrams can get a little bit busy. Hope that kind of helps you understand. So only 2 electrons in any orbital. That's a rule. And you might want to jot that down right now. I think it's in the notes a little bit later, but we're talking about it now. So you can write that down here. So only 2 electrons can exist in any one orbital. You can't shove 3, 4, 5, 6 in there and not in one orbital. They have to go to the next available space, the next available orbital. Okay, so does everyone kind of see that for neon there? All right. Now, if we're talking about oxygen right here, then obviously there would be, one of these orbitals would be empty. You'd have 2 less electrons. Okay. Well, here's the thing. Drawing the orbitals like this, you're not going to be really doing this for each, because if you get to, gadolinium or whatever down here, you can't draw all those orbitals. So we're not going to be, I'm just trying to show you a different way. But you could draw the empty orbital, yes. Okay, that would be good. But yeah, like I said, you wouldn't have to. We're going to mainly do representations like this. For neon, it's going to be like the 1s, and you're just going to say there's 2 in there. The 2s gets filled next, and that's completely full. And then the next is the 2p, and that's completely full, and so you would put a 6 there for neon. So this is going to be the common notation. But again, I'm going to focus on that just a little bit later. I'm kind of jumping ahead of myself a little bit, showing you this orbital notation here. All right. But let's just get back to filling order specifically, okay? So we've got the 1s, and then the 2s, and then the 2p, okay? So getting back to it, now we have the, I'll do that in black, 3s is next. And then we go over here, and guess what this would be over here? This is the 3p. The 3p orbitals. And yes, you have 2p orbitals, you have 3p orbitals, you have 4, 5, 6, 7p orbitals. And so what I'm going to do now is I'm going to show you that these elements here, the placement here, represent all s orbitals. So you can go ahead and, if you want, fill this in on your... So those are the 4s orbitals right there. The 4s. These are all of the s orbitals on the left side there. Okay? All right? So again, we're moving left to right across the periodic table, and this is the filling order. So 1s, then 2s, then 2p, then 3s, then 3p, then 4s. You getting it? Now this is where it gets a little bit wonky. Okay? This is where it gets a little bit wonky. These ones in here, these orbitals in here, and yeah, I'll just outline this right here. These orbitals here are the d orbitals. Okay? The d orbitals. And there are 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Now remember, there are 5 kinds of d orbitals. And if 2 electrons can go in each orbital, that's 10 electrons. So here are your 10 electrons that completely fill the d orbitals for each level. So again, back to filling order, we've got 1s, then 2s, then 2p over here, then 3s, then 3p, then 4s, then this is actually energy level 3 d orbitals. Okay, actually they're energy level 3 d orbitals. Now, the third energy level has s orbitals, p orbitals, and d orbitals. It just so happens that the 4s orbitals get filled before the 3d. Okay? And if you look at the periodic table and follow left to right along the rows, you'll never get this mixed up. Okay? But the electrons that are in the 4s are slightly less energy than in the 3d. So yes, so from scandium to zinc is all 3d there. Yep. Okay, then we're back to 4p. So after 3d is 4p. Then after 4p is 5s. Then this is 4d here. Okay, and I'll just finish this real quick. Okay, so that's sort of the orbitals according to the periodic table. And again, what you have to remember is you go left to right always, and then that's the filling order, whatever you see. So after 3s, that is not the 3d because it's not in the same row. You see that? So 3s skips all the way over to 3p, then 4s, then 3d. Okay, got that? All right, now what about these ones down here? I mentioned that earlier, and these are the f orbitals. And it starts right here, right? These rows are plucked out of the periodic table here. If this was, written all in one spot, the periodic table would be super wide because these rows would have to fit here and here respectively, right? So that's why they're plucked out of the periodic table there. The big rows are put at the bottom so they can squish up the top part. But after the 6s, then we see that these elements come next, right? After this one, we go down here. And so these are the f orbitals. The f orbitals. And this is the 4f orbital. This is the 5f orbital. So if we look at something like cerium here, okay? Right here, number 58. If we take a look at that, the filling order for all of the electrons, there's 58 of them, right? There's 58 of them in cerium. The filling order would be as follows. 1s is first, then 2s, then 2p, then 3s, then 3p. All of these get filled with all these electrons. That's where they go. Remember, this is their hotel rooms, right? They're filling the bottom floor first, 1s and then the 2s. Then they go to the 3s, 4s, then 3d, then the 4p, then the 5s, then the 4d, then the 5p, then the 6s, and then the final 2 go in the 4f orbital. Make sense? It might be helpful to think of the electrons all standing in a line outside of the orbital hotel. And they have to go in 2 at a time, right? So 2 go into the 1s, okay, now the next 2 go into the 2s, now the next 2 go into one of the p orbitals, then the next 2 go, Now, I'm going to adjust that a little bit later because in the filling order with the p's and the d's and stuff like that, one orbital doesn't get completely filled first. Actually, they actually half fill orbitals first, and then they start completely filling on the p orbitals. But I'll explain that here soon. But that's the general idea of it.